The reaction of 15 gram of an NPO sample of calcium carbonate with excess hydrochloric acid of concentration 1 mole per decimeter cube is used to investigate the rate of a reaction. And then we're given the balanced equation for the reaction. And then it goes on to say that the volume of CO2 produced is measured at regular intervals. And then we have the sketch with the volume of the CO2 on the y-axis and the time on the x-axis. And then the first question, 5.1, says define the term reaction rate. We know that the reaction rate is the change in concentration of the products per unit time. The change in concentration of the products per unit time, or the change in concentration of the reactions per unit time. So that is given by the reaction rate equals to the change in the concentration of the products per unit time, or the change in the concentration of the reactants per unit time. I hope you get that. And then 5.2 says, give a reason why the gradient of the graph decreases between T2 and T3. This is the part we're talking about that I just highlighted in yellow on the left hand side. The question is saying, give a reason why the gradient of the graph decreases between T2 and T3. Because now we are at T2 and we're going to T3, the amount of the reactants is getting depleted, right? So from T2 to T3, the gradient is decreasing because the amount of the reactants is getting depleted and the reaction rate is going down, right? So the amount of the reactants is getting depleted, and as a consequence the reaction rate is going down. And then we can move to 5.3. We have 5.3.1, and then it says changes in the graph between T1 and T2 are due to temperature changes within the reaction mixture. And then 5.3.1 says, is the reaction exothermic or endothermic? The reaction is exothermic. It's exothermic. Why are we saying that it's exothermic? Because the temperature change is within, right? And then from T1 and T2, the reaction rate increases. Okay, so let me go a bit deeper on that and further try and explain the concept. So in an exothermic reaction, there's a temperature change within, right? The temperature within increases. And then we know that if we increase the temperature in a reaction, the reaction rate goes up, right? And then from T1 to T2, we have a very steep gradient, which shows that the reaction rate is high, right? So the only time a reaction mixture will increase its internal temperature, it's if the reaction is exothermic. And then let's move ahead and go to 5.4. 5.4 says the percentage purity of the sample is 82.5%. And then calculate the value of X on the graph, assuming that the gas is collected at 25 degrees Celsius. So we have T equals to 25 degrees Celsius, and the molar gas volume Vm equals to 24,000 centimeter cube. So we're supposed to calculate the volume of CO2 at X. You can see that at X, that's where the graph start flattening out, right? So what does the graph flattening out tells us? It tells us that at X, the reaction is complete, right? But then, we have, CO3, calcium carbonate plus 2HCl, right? We know that the HCl is in excess. So the reaction will complete when, the calcium carbonate is depleted. So we cannot use, sorry, here I wrote HC instead of HCl. We cannot use the number of moles of HCl to determine the number of moles of CO2 because the HCl is in excess. Even after the reaction is depleted, we still have HCl. But then we can use the number of moles of calcium carbonate to determine the number of the corresponding moles of CO2 that we're going to have. And then after we find the number of moles of CO2, we can then convert that to the volume and determine the value of X. So we're going to start by calculating the number of moles of calcium carbonate because we have the mass, right, and the percentage purity. So the first thing we're going to do, we're going to say that the mass that's reacted is equals to the mass initial multiplied by the percentage purity, right? So that will be equals to, we know that the initial mass is 15 grams multiplied by 82.5%, which is going to give us, so 15 multiplied by 82.5%, that gives me 12.375 grams. So that's the mass of calcium carbonate that reacted. And now I can convert this mass to the number of moles. And then from there, I can then find the number of moles of CO2 produced, which I'll therefore be able to find the volume, which is the X we are interested in. So we know that the number of moles equals to the mass divided by the molar mass. What is the mass? The mass is what we just determined right now, which is 12.375 gram, and then we're supposed to find the molar mass of calcium carbonate. So let me pull up my periodic table and see what that leads us to. So for calcium, we have a molar mass of 40, and then for carbon, that's 12, so that's plus 12, and then for oxygen, that is 16, but then we have 3 oxygen atoms, so that's 16 times 3, which is going to be 12.375 divided by 40 plus 12, that's 52, plus 16, 32, 48. So we have 52 plus 48. So we just have 12.375 divided by 100, which is giving me 0.12375 moles, right, of calcium carbonate. And now we can relate the number of moles of calcium carbonate to the number of moles of CO2 using our balanced equation. We know that the number of moles of the calcium carbonate divided by the number of moles of CO2 will be equals to 1 divided by 1, right? 1 being the balancing coefficient in our balanced equation. We can see that we just have 1. We don't have a number, but we know that we have 1 there on calcium carbonate, and then on CO2 is also true. For the number of moles of calcium carbonate, we say that it's 0.12375 divided by the number of moles of CO2, and then this is just equals to 1 divided by 1, right? So the number of moles of CO2 equals to 0.12375 moles. So now we have determined the number of moles of CO2. We can then find the volume of CO2. But then how do we find the volume? We know that you can determine the number of moles by dividing the volume by the molar gas volume, right? So we have N equals to V divided by Vm. We know what the number of moles is. That's 0.12375 equals to the volume divided by the molar gas volume, which is 24,000. So if we cross multiply the two, we can then determine our volume, the value of X. So we're gonna get V equals to 0.12375 multiplied by 24,000. And then let me put that in my calculator real quick and see what I get. Multiplied by 24,000. That is giving me 2,270 centimeter cube. So the value of X for our equation, that is 2,970 centimeter cube. So let's carry on and do 5.5. 5.5 says, how will the reaction rate change if 15 grams of a pure sample of calcium carbonate? Initially, the mass that was pure was 12.375 grams. Now the mass that is pure is 15 grams. So what will happen to the reaction rate? The reaction rate will increase. And then 5.6 says, explain why you say it is increasing using the collision theory. So we know that if the mass increases, we're gonna have more particles, right, that are ready to react. And then with more particles, we'll have more collisions per unit time. And then as a consequence, the rate of the reaction will go up, right? Will be high. So that's how you'd explain 5.5. Calcium carbonate is reacting with excess dilute hydrochloric acid, right? And then that is used to investigate one of the factors that affect reaction rate. And then we have some balance equation, right? And then it goes on to say the same mass of calcium carbonate is used in all the experiments, and the temperature of the hydrochloric acid in all experiments is 40 degrees Celsius. And then we have a table there for experiment A, B, C, and then 5.1.1 says, for this investigation, write down the dependent variable. So if you read the question again, you will realize that it says used to investigate one of the factors that affect reaction rate. So the dependent variable here is the reaction rate, because it's what we are investigating, right? The factors that affect the reaction rate. And then 5.1.2 says what is the independent variable? So independent variable is more like, what are we changing to investigate that which we're investigating? If you look at our table, in experiment A, we used granules for calcium carbonate, and then for experiment B we used lumps, and for experiment C we used a powder, right? So the independent variable here is the surface area, because it's what we're changing to determine its effect on reaction rate. And then it goes on to say the carbon dioxide gas CO2 produced during experiment A is collected in a gas syringe. The volume of gas is collected. The volume of gas collected is measured every 20 seconds, and the result obtained as shown in the diagram below. And then we can see the diagram clearly. And then we have 5.2 and 5.2.1. 5.2.1 says what can be deduced from the graph regarding the rate of the reaction during the time interval. And then for 5.2.1 we have 20 seconds to 40 seconds. So let's go and look at this time interval. So from 20 to 40, it starts flattening out, right? It's not really flat, but it's no longer as steep as from 0 to 20. So we can see that reactants are getting used up, right? Are getting used up, and then as a consequence, the reaction rate is decreasing. And then 5.3 says calculate the average rate in centimeter cube per second at which CO2 is produced in the experiment. So for CO2 we are given the volume, right? So our reaction rate will be the change in the volume divided by the change in time, and then we want the average. So when we want the average, we have to consider the entire time interval. If it says between 20 and 40, then we'll just use the interval 20 and 40. But then it said the average, so we have to use the entire interval. So we're gonna have volume final minus volume initial equals to T final minus T initial. So what is the volume final? The volume final is 500 centimeter cube, right? So we're gonna have 500 minus by 0, because initially it was 0, right? And then we're gonna divide that by T final, which is 60 seconds, and then minus 0 seconds, or second, so to say. So let me just punch that in my calculator. So we have 500 divided by 60 in a way, which is 8.33 recurring centimeter cube per second. And then we are done. And then we can move to 5.4, which says how will the volume of CO2 produced in experiment B compared to that produced in experiment A? Choose from greater than, smaller than, or equal to. This is a tricky question, because let's look at experiment A and experiment B, right? So we have the same volume of HCl for A and B, same concentration of HCl, and then instead of granules, they're using lumps, right? So the reaction rates will be different of these two reactions, but then at the end of the day, the volume of CO2 at the end will be the same, because it is said that they use the same mass, right? So for one reaction, to be more precise, experiment A, it will complete quicker than experiment B, but then at the end of the day, they're gonna produce the same amount of CO2. So the answer is equal to, right? And then we can move on to 5.5. 5.5 says a graph is now drawn for experiment C on the same set of axes. How will the gradient of this graph compare to the gradient of the graph for experiment A? So this is experiment A, right? And then this is the graph, and they use granules. So experiment C is powder. So we expecting experiment C to shoot up also, right? Let me use a thinner line to also shoot up, but then the reaction ends quicker compared to experiment A, where they're using granules. So our question is asking us about the gradient. So we're gonna say that the gradient will be greater than, right, which sound a bit weird. It will be greater than in value, but it's not very scientific. It's the gradient will be steeper, yeah, but then, well, that's what they want from us, so it's greater than. And they're saying that let's back it up using the collision theory. So again, experiment C is powder, right? And experiment A is granules. So basically, in experiment C, there is more surface area. And as a result of more surface area, we have more particles that are exposed, and then we'll have more effective collisions per unit time, and as a consequence, the reaction rate will increase, right? And then now we can move to 5.6, which says, assume that the molar gas volume of at 40 degrees Celsius is 25.7 decimeter cube per mole. Calculate the mass of CaCO3 used in experiment 1. So the information we have is information about CO2, right? So if we determine the number of moles of CO2, then we will use the balancing coefficients to determine the number of moles of calcium carbonate, and ultimately calculate the mass, right? So we can say the number of moles of CO2 is equal to the volume divided by the molar gas volume. So what is the volume of CO2? Let's check. It's 500 centimeter cube, right? So we're gonna say 500 divided by 1000, converting to decimeter cube, divided by what? By 25.7, like we are told. So we have 0.5 basically divided by 25.7, which is equals to 0.01946 actually moles. So now let's go to our equation. So now we can see that the number of moles of CO2 will be equal to the number of moles of calcium carbonate, right? Because the balancing coefficients are the same. So this will be 0.01946. So the mass will there be for the number of moles multiplied by the molar mass. So we have 0.01946 multiplied by 100. This will give you 1.946 grams.
Two experiments, 1 and 2, are conducted to investigate one of the factors that affects the rate of the reaction of aluminum carbonate with excess hydrochloric acid. And then we have the balance equation there for the reaction on the left hand side. Let me just go ahead and write it down. So just give me a second. Plus 6 HCl is going to give us 2 Al 3 H2O plus 3 CO2. And then we have the setup in the image given there. There we have the hydrochloric acid. I think it's been put in slowly, and then we have the aluminum carbonate at the bottom, and then we have a syringe. So one of the products here is a gas, right? So that means that all the gas that will be released as the reaction is taking place is gonna end up in the syringe. The syringe will be sucking out the gas, right? So we're given some information for experiment 1 and then some information for experiment 2. And then the first question says 5.1, define the term rate of a reaction. That is the change in concentration of the products or reactants per unit time, right? The change in concentration of the products or the reactants per unit time. So formula wise, you write it like this: the rate of the reaction equals to the change in the concentration of the products per unit time. And then 5.2 says, using the experimental setup above, state the measurements that must be made to determine the rate of this reaction. So again, look at the picture on the left hand side. Look at the setup. As I've already stated, one of the products of the reaction is a gas, right? It's a gas. And then the time, you can always measure the time manually, right? So for you to calculate the rate of a reaction, we know that this is we need the change in concentration of the products of the reactants divided by unit time. So one of the things you will need to measure, obviously, is delta T, which you measure manually. Maybe you use a stopwatch or something. And then now the change in products or reactants. That's sort of like the trick of this question. Because we have this syringe here on the question, on the setup. We are going to measure the volume of the gas that is released. The gas is one of the products, right? So that's how we will use this equation to calculate the rate of this reaction. So the answer will be, we need the time, which we're going to measure manually, and then we need the volume of the gas, right? Volume of the gas, of which we're going to determine from the syringe. Syringes, usually they have like what do you call this? They already have markings on them that show the volume and stuff. So you just measure the time, and then the syringe will give you the volume of the gas, and then from there you can calculate the reaction rate. Let's move forward. 5.3 says, using the collision theory use the collision theory to explain how the average reaction rate in experiment 1 differs from the average rate in experiment 2. So if you pay attention here, in experiment 1, they use a volume of 100 centimeter cube for 1.5 mole per decimeter cube of HCl, and then for experiment 2 they use 50 centimeter cube, and then the concentration is 2 moles per decimeter cube, right, of HCl. So now the question is saying, let's use the collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. So here you can see that here there's less volume, right? Yeah, less volume will mean greater concentration, because concentration is inversely proportional to volume, right? And then here we have more volume. So the rate of reaction of experiment 2 is greater than the rate of reaction of experiment 2. Experiment 2 will take less time because there is more molecules, right? So to put it nicely, the first point you'd say that more HCl particles, right? There will be more HCl particles because the concentration is higher. And then what does more particles give us? More particles give us more effective collisions, right? And then what will more effective collisions give us? Effective collisions is a prerequisite of a reaction, right? So the more the effective collisions, the higher the reaction rate. So the reaction will take less time. And then I've gone through this on a video I made in the past. I'll put it up here. If it will pop up in the screen, you can click and watch it. Here it is on the top left hand side of the screen. Let's move ahead. On that video, I talk about how other factors affect the reaction rate, like the surface area, the pressure of a gas, and all that nice stuff. And then 5.4 says the average rate of the reaction in experiment 2 during the first 2.5 minutes is 4.4. So let's write that down. We have delta T, which is 2.5 minutes. Right, and then we have the average rate of reaction, which is 4.4 times 10 to the minus 3 moles per minute, right? And then the question says calculate the number of moles. So we need the number of moles of what? Let me see, of aluminum carbonate. So that is, let me just write down the formula. Then we have CO3 there, and then we have this 3 there. So we need the number of moles of this aluminum that remains in the flask after 2.5 minutes. So after 2.5 minutes, the reaction is not completed. The question then says, what are the number of moles that are remaining? So, okay, we know that the rate of a reaction is given as the change in the concentration of the products divided by the time it takes. We have the reaction rate, it is given to us. We have the change in time, the time it takes for the reaction to get to our point of interest. And then now, if we can calculate this change, right? This change here, then we can then be able to calculate the number of moles. But then even if we were not able to do that, it's the information we have. We had to start there, and then we'd look for, other ways of doing the question. I'm still gonna do more questions on this topic. So if you wanna see more of that and how we tackle different problems, subscribe to the channel and like the video. So, okay, let me move on. The reaction rate, it is said to be 2.5 minutes, and then the change in the products is what we're given. But then if you pay close attention here, aluminum carbonate is actually not the product, but the reactant, right? So here we're supposed to have of the reactant, and then, okay, there we go. Divided by actually I put time where it's not supposed to go. Time is supposed to go here 2.5, and then here we have the reaction rate 4.4 times 10 to the minus 3. That is the same as divided by 1000, right? And then now if you make this reaction, this change in the concentration of R, we get 2.5 multiplied by 4.4, everything divided by 1000. So let me go ahead and put that in my calculator real quick and see what I'm getting. So we have 2.5 multiplied by 4.4 divided by 1000. That is giving me 0.011. So what's the SI unit now? We're getting 0.011, but then what's the SI unit? We know that 2.5 is in minutes, right? And it's been multiplied by the reaction rate, which is in, what's the SI unit? Which is in mole divided by minute, right? So the minute and the minutes cancel out. So the change in the concentration, in the number of moles, is thus 0.011, right? So that's how we are getting to how I'm getting to 0.011. 0.011 moles instead of moles per decimeter cube. Number of moles in excess equals to, I'm going to explain why I'm doing this in a second, right? Equals to 0.016 minus 0.011, which will give us 0.005 moles in excess, right? So why I'm doing it like this, let's say you have 8 apples, right? And then here you've eaten 0, and then after some time now you don't have after some time you have eaten 2 apples, right? So, and then you're like, what's the change in the apples that I had initially? You're going to subtract the number of apples you started with by the change in the apples you eaten. So here you had eaten 0, now you've eaten 2. So you're going to say 5 minus 2, which will give you 3. And then the 3 will be the axis. So the same thing with this question. That's the same idea I'm using. Now let's move to 5.1. 5.1 says calculate the maximum volume. So we have a volume of CO2 that can be prepared at a temperature of 25 degrees Celsius in experiment 1. Take molar gas volume at 25 degrees Celsius as 24,000 centimeter cube per moles. Okay, we know that the number of moles can also be given by the volume divided by the molar gas volume. So right, so that is N equals to V divided by Vm. In this question we are given Vm, the molar gas volume, as 24,000 centimeter cube per moles, and then the question says let's find the maximum volume. So this is what we are interested in, and then what we don't have is the number of moles, right? So if we determine the number of moles, we can then use this formula to calculate the maximum volume of CO2 that can be prepared for experiment 1, right? But then to find the number of moles, it's not really complicated because we can use the equation to do so. We know that in our balanced equation, we have CO2 which is balanced with by 3, right? And then we have aluminum carbonate, which is CO3, and then we have that 3 on the outside, which is balanced by nothing, which is basically just 1. So what we can do here, this is the number of moles, this is the number of moles. We can calculate the number of moles of CO2, not CO3, I'm sorry for that. We calculate the number of moles of CO2 by cross multiplying. So we're gonna get the number of moles of CO2 equals to 3 multiplied by the number of moles of aluminum carbonate, right? That is 0.016, right? Because the number of moles of aluminum carbonate is 0.016, and then the HCl is in excess. So at the end of the day, all the aluminum carbonate is going to get used up. So this will give us, let me just put that in the calculator real quick. That is going to give us 0.048 moles. So now we have the N we were looking for here. Now we can just calculate V, right? So we're going to say V equals to the number of moles multiplied by the molar gas volume, which is given as 24,000. So we're going to have 0.048 multiplied by 24,000 mole per decimeter cube, right? And then the SI unit of this is
we have an SI unit of mole for moles, and then here is mole per decimeter cube, right? So moles and mole cancel out. We end up with, let me put that in the calculator real quick, 24,000. We end up with 1,152. Am I doing that right? Yeah. 1,152 decimeter cube. Oh no, I just realized that the number, okay, I wrote this wrong. I just realized that here it is given as a centimeter cube divided by mole, right? So mole and mole cancel out, and then we are left with centimeter cube. 5.1. So we're given a Maxwell-Boltzmann distribution curve for a certain reaction, and then we have Q on our y-axis, we have P on our x-axis, and then we have some point R, right? And then 5.1.1 says P and Q are the labels on the axis. What quantity is represented by P? We know that on the x-axis of the Boltzmann distribution curve, we have kinetic energy, right? So 5.1.1 will be kinetic energy. And then 5.2.2, we are supposed to give the name for Q, which is the number of particles. The number of particles. Yeah, this is the same curves we use when we determining the factors that affect a reaction rate, right? And then if you haven't done that, look at the description. I'll put a link to a video where I was explaining that. And then 5.2, it says line R represents the minimum energy required for the reaction to take place. And then 5.2.1 says write down the term of the underlined phrase, minimum energy required for the reaction to take place. That's the activation energy. Activation energy is self-explanatory because activation energy, so to say. And then 5.2.2 says, how will the shaded area on the graph be affected when a catalyst is added? Choose from increase, decrease, or remain the same. Now, obviously, it's going to increase, right? Increase. And then I'm going to explain that in a second. Actually, 5.3 asked me to explain why I'm saying it increases. When you add a catalyst, it provides an alternative path, right? So let me just write that down. Alternative path of lower activation energy. Activation energy. So after we have an alternative path of lower activation energy, then more particles will have enough kinetic energy to react, right? Yeah, to react, and as a consequence, we will have more effective collisions, and then yeah, the reaction rate gets high, right? And then you have your 4 marks. When you add a catalyst, the alternative path, there will be an alternative path of lower activation energy. So particles that previously didn't have enough EK, now they do, and they will form reactions, right? And then the more the number of reactions, the more the number of effective collisions, and then the reaction rate will go up. And then we move ahead to 5.4. So we have a reaction between powdered calcium carbonate and excess hydrochloric acid. It's used to investigate reaction rate at 25 degrees Celsius. And then we have a balanced equation down there. And then several experiments are conducted using the same mass of impure calcium carbonate, and then with different initial concentration of dilute hydrochloric acid. Then the graph represents the results. And then, okay, it is said that we should assume that there are impurities that do not react. Okay, fine. And then 5.4.1 says controlled variable. By control variable, they mean the variable that is constant, is not being changed in any way, right? So if you pay attention to details, when I was reading that statement, it said same mass of calcium carbonate. I just highlighted it in blue on the left hand side. Same mass of impure calcium carbonate. So for 5.4.1, we'll have mass of CaCO3, and then that's the one option you have. And then the other option you have is the temperature, right? They didn't say anything about the temperature, so you can go ahead and see that. And then 5.4.2 says let's have a conclusion for this investigation. Okay, look at the graph. Look at the x-axis. As the initial concentration of HCl is going up, the average rate of production of CO2 is also going up. And CO2 is our product, right? So that means that concentration is directly proportional to reaction rate. As we increase the concentration of HCl, the average rate of production of CO2 increases. We have more CO2, right? So that means the reaction rate is higher. And then let's move ahead to 5.4.3. It says the calcium carbonate in 6 grams of the impure sample reacts. So we have CaCO3, and then that which is pure is 6 grams, right? And then they say that it reacts with HCl, obviously, of concentration 0.03 moles per decimeter cube in 26 minutes. So we have delta T equals to 26 minutes, right? And then 5.4.3 goes on to say, use the information in the graph to calculate the percentage purity of the calcium carbonate. So we want to calculate the mass of the impure calcium carbonate, and then after we do that, we can go back and calculate the percentage purity. Then they say, assume that the molar gas volume at 25 degrees Celsius is V molar gas 24,000 centimeter cube. So, okay, let me just write down the equation down again. So we have calcium carbonate plus 2HCl giving us, okay, let's ignore all the other products and just put CO2, right? Because CO2 is what we're interested in, because that's what we were measuring. So the question is saying, let's calculate the mass of CaCO3, right? And then what do we have? So for CaCO3, we only have the mass of the pure substance, right? And then for 2HCl, what's the information we have for HCl? We only have the concentration. And then for CO2, we have the molar gas volume, we have the average rate, we have the reaction rate, so we have the reaction rate, and then we have the time of the reaction. So it seems like CO2 is what we can use to calculate everything else, because this is where we have the most information. So we can use the reaction rate to calculate the volume of CO2, right? And then after we have used the reaction rate to calculate the volume of CO2, we can use the volume of CO2 to calculate the number of moles of CO2. After we've calculated the number of moles of CO2, we can use the number of moles of CO2 to calculate the number of moles of CaCO3 and ultimately calculate the mass. The thing about this question is that there's no formula I can give you to use in every situation. You have to read the question and understand it, and then you can take it from there. So we know that for a gas, the reaction rate is equal to the change in the volume divided by the change in time. And then if we take this bullet point at the top, where HCl is 0.03, the average rate of production is 50 centimeter cube per minute, right? So we're gonna have 50 equals to the change in volume divided by the change in time. We are told that it takes 26 minutes, so we're gonna have 26 here. And then if we cross multiply, we're gonna get the volume equals to 50 multiplied by 26, which is gonna give us 50 multiplied by 26. That is 1,300 centimeter cube, right? So now we have determined the volume of CO2, like we said. The second step is now to determine the number of moles of CO2. And that is given by number of moles equals to the volume divided by the molar gas volume, which is equal to the volume we just determined is 1,300, and then the molar gas volume is 24,000, right? And that is equals to, so we have 1,300 divided by 24,000, which is giving us 0.05417, right, moles. So now we can use the number of moles of CO2 to determine the number of moles of CaCO3 that reacted using the ratio of the balancing coefficient, right? So from our equation, we know that the number of moles of CO3 divided by the number of moles of CaCO3 is equals to 1 divided by 1, right? Because those are the balancing coefficient. So the number of moles of CaCO3 will just be equal to the number of moles of CO2, right? So that will be also 0.05417 moles. So now we've done step 2 to calculate the number of moles of CaCO3. Now we can take a formula and calculate the mass of CaCO3. So we know that the number of moles is also equal to M divided by the molar mass, right? And then we want the mass. So the mass will be equal to the number of moles divided by the molar mass, which is equal to 0.05417 multiplied by, let me check the number of moles of CaCO3. That is 100, right? You can check it on the periodic table. So we're gonna have, let me just put that in the calculator real quick. And then that will be equals to 5.417 grams, right? So now we have the mass of CaCO3 that reacted and the mass of the impure sample, right? So to find percentage purity, we're gonna say it's percentage purity equals to pure substance divided by impure, right? The whole substance. So this is going to be equals to 5.417 divided by 6, which is, let me just put that in my calculator real quick, which is equals to 0.9027. And then after that, you can just multiply that with 100 so that you get it in percentages. So that will be 0.9027 multiplied by 100. That is 90.27%.